with tonight's exercises. So we are recording the session, and first we want to find a power series representation for this function. I'll give you a moment to copy that. All right, so we want to find power series representation for the log of 5 minus x. And we already know something about x, right? What would x certainly have to be greater than? Well, actually, x would have to be, let's see here. For what's the domain of this function? We can't have the log of a negative number. So that means 5 minus x would have to be positive. So that's right. You can't have, that's right, John, 5 minus x can't be less than 5. So let me just make a note here on this. So 5 minus x has to be greater than 0, which means x has to be less than 5. Okay, so that's the domain of the function. However, it may not be the domain or interval of convergence for the power series for this function. So okay, so we remember the Apple formula. We remember the Apple formula that we had yesterday. 1 over 1 minus an apple is equal to the summation. My hands are just tired from working here. Equals the summation where n goes from 0 to infinity of apple to the nth power. All right. That was based off of the geometric series derivation that we did from section 8.6. Just looking at it here real quick. Right. And of course, this holds true if this holds true when the absolute value of the apple is less than 1. All right, so that's a formula we know and love. But when we look at this function here, unlike the functions and problems that we had yesterday and the ones you worked in your homework, the log of 5 minus x, I mean, I can't just, off the, like in my mind, I can't relate the log of 5 minus x directly to my Apple formula here. So, but yet the problem says find a power series representation. So what we have to do is we have to manipulate the function by doing something. Well, yesterday we took the derivative of a function and it helped. So let's consider taking the derivative of the log of 5 minus x. Okay, so we'll move to the next page here. So if we differentiate the log of 5 minus x, by the chain rule, we're going to get 1 over 5 minus x times negative 1. Okay, therefore, the derivative of the log of 5 minus x is negative 1 over 5 minus x. And so by taking the derivative of this function, I get the derivative. I can see in my mind how I can expand that as a power series using the Apple formula. I can see that in my mind. Okay, so far are we okay? Are there any questions so far? All right. Well, so this is nice, but remember what we're interested in is the log of 5 minus x. That's the power series. We want a power series for that function. Well, how can I get the log of 5 minus x back from the left-hand side? What can I do to the left-hand side? What operation can I do on the left-hand side so that I will get the log of 5 minus x? Who thinks they could chat that out? Let's see, hold on here. Oh, that's right, Robin, very good. We can integrate. If we integrate the derivative, we'll get the function back. Okay, if we integrate the derivative, we get the function back. Okay, so we'll do that. We'll integrate the left side and the right side. So by integrating both sides of this equation, then the left side becomes now the log of 5 minus x. Okay. Now, technically, there should be a constant here, okay? But let's just, we know in the end we're going to get it. We know in the end there's going to be a constant of integration. But technically there should be, I guess, let me just see here. There should be some constant here, right? All right, so now what I'm going to do, since I have the log of 5 minus x plus this constant, and the constant I can just move over to the other side in the end. But now I am going to integrate 1 over 5 minus x. I bring the negative out front. But 1 over 5 minus x, of course, I can write that as a power series using the Apple formula. So I factor 5 out, okay? And then I have 5 times 1 minus x over 5. So I got the constant here too. Make a note here. Okay. So are there any questions up to this stage here? All right, well, so what's my apple going to be? And for this rational function here, this rational function, what's the apple? That's good, Robin, x over 5. So, well, let's proceed on then. Let's proceed on. Are we good with this page? May I move to the next page? Okay. Well, we'll move to the next page. So now I have that constant of integration from the left side plus the log of 5 minus x equals negative 1/5 times this integral, and then the x over 5 is the apple. And so now I just apply the apple formula right here. And we make note that the interval of convergence is going to be from negative 5 to 5. Okay. Okay, so now what we want to do is we have x over 5 to the nth power here. I'm going to write that as x to the nth over 5 to the nth. So now we have c plus the c1 plus the log of 5 minus x equals negative 1/5 times the integral of this series here. But we know that the integral of f plus g, okay, dx, we know that the integral of f plus g dx is equal to the integral of f dx plus the integral of g dx. It's just a simple way of saying that the integral of a sum is the sum of the integrals. And so we can rewrite we can rewrite this expression like this. And you notice how I show the work. The textbook solutions may not show all that work, but I'm going to look for that work on this fourth exam. Okay, it will be part of the credit for the problem. Because I need to make sure you understand the concepts. Okay. Are there any questions going to this stage here? We had the integral, we had -1/5 times. Okay, we won't worry about the -1/5, but we had the integral of a sum. The integral of a sum is the sum of the integrals. Okay, does this maybe give me a thumbs up if this step makes sense, going from here to here. John's comfortable, okay. Josiah's comfortable, great. Robin's comfortable. Is anybody a little uncomfortable? All right, all right. Well, so naturally, we need to integrate. We need to integrate this. In the integral here, in the integral, what is treated as a constant in that integral? You have the integral of x to the nth power over 5 to the nth power dx. So what's treated as a constant there? What can we treat like as a constant? That's right, John, the 5 to the nth power. Our integrals with respect to x, 5 to the nth is a constant relative to the integral. So we can factor it out. So now we have -1/5 times the integral, where n goes from 0 to infinity, of 1 over 5 to the nth power times the integral of x to the nth dx. So you're adding up a bunch of integrals, an infinite number of integrals. That's what you're doing. The antiderivative, of course, of x to the nth, we're going to use the reverse of the power rule. And so you're going to get this. Now, so what we have is we have the log of 5 minus x plus C1 equals this plus C2. So what's happening is when you're going to have the sum of an infinite number of indefinite integrals. Every indefinite integral will produce a constant, but all those constants together I call C2. Okay, are there any questions up to here? Okay. Well, so therefore, the log of 5 minus x will equal then what we have on the right here. And the constant c is equal to C2 minus C1. What I also did was the 1/5, I brought it inside the summation. We can bring constants inside the summation. Now you notice well, hold on. Let's catch up a little bit here. Let me circle the, this is some of the most beautiful math, I think, you know, that I've seen. I mean, I've seen a lot of math, right? I have a PhD in math, but I always feel that series are just very beautiful. And they're used, there's so many applications. Okay, so you notice that the index starts at n equals 0. Right, the index starts at n equals 0. But we can, if we want, we can change the index to n equals 1. So when we do that, what we have to do then is all of the n plus first terms, all of the, like, well, every time you see an n plus 1, you replace it with an n. And that's what you did here. And by having the series start its index at n equals 1, you just get a little bit nicer looking formula. Are there any questions so far? Okay, okay. Well, so there's one thing left to do. We have to solve for this constant c. The log of 5 minus x is, you know, it's dependent on x. And we have a constant here, but we can solve for that constant, right? We can solve for it. So what we do is we're going to pick a value of x. And the easiest value of x to pick is x equals 0, because when we substitute x in, we have to substitute x into the power series as well. So if we substitute x equals 0 in, we can solve for the constant very easily. So the log of 5 minus 0 is equal to this negative sum, and you notice where the x was, I put in 0, because now I'm demanding that x equals 0. Now you could put in a different value like x equals 1, but then, or something, and you'll get the same. I mean, well, let's not talk about that yet. You put in x equals 0. This whole sum is like adding a bunch of zeros, and so your constant equals the log of 5. And therefore, you have your power series representation for the log of 5 minus x. And I was going to just mention, we picked x equals 0, and that's traditional when you're solving for the constant with the power series. If we were to pick like x equals 1, we could get the constant that way, but it would be tremendously harder, because you'd have to figure out what the sum is of all the terms in the power series, and it would just be harder. Do what's easy, right? Do what's easy. All right, let's make sure everybody's comfortable here. All right, so the log of 5 minus x is equal to negative sum n equals 1 to infinity of 1 over 5 to the nth power times x to the n over the nth over n plus the log of 5. And notice that the function equals the power series only when x is between negative 5 and 5. So the power series converges over that interval. And that interval is the domain of, well, it's the domain of just the function itself, log of 5 minus x, is x is less than 5. But the domain of the log function relative to the log function being equal to the power series, you would restrict x to be between negative 5 and 5. All right, are there any questions on that before we move to our next example? All right, I'll move to the next example. Does everybody have the notes okay? Okay, let's move to the next example. All right, here we want to express this indefinite integral as a power series. All right, I'll let you copy it down. Okay, so we want to express this indefinite integral, which is the integral of x minus the arctangent of x over x cubed dx. We want to express that as a power series. Offhand, what's kind of the hardest part of the problem? What's the part of the problem that you might be most uncomfortable with? And there could be several answers, but certainly when I saw this, there was a part that had me thinking. Yes, I agree, John. The arctangent. So if we're going to express the definite integral as a power series, then we have to find a power series for the arctangent of x. And what we can do is recognize, well, the arctangent of x does happen to be the integral of 1 over 1 plus x squared dx. And that's a good thing. That's a good thing, because 1 over 1 plus x squared, we can write that as a power series using our Apple formula from section 8.6. We can write that as a power series. So the 1 plus x squared we'll write as 1 minus negative x squared. And then we apply the Apple formula. And we'll get back to the original integral here. I'm just trying to find a power series for the arctangent of x. The book shows this in the 7th example, but they leave out steps that I think are helpful for you. Okay, so we have the integral of the sum, n equals 0 to infinity, of negative x squared to the nth power. Of course, I'm going to simplify the inside here. Negative x squared is the same as negative 1 times x squared. Okay, and then I can rewrite the integrand, the power series, like this. Whoops. Let me know if you have any questions so far up to this step. You've seen this kind of thing before, so you worked with your homework yesterday. Okay. All right. So we have that the arctangent of x equals the integral of the power series. But remember, the integral of a sum is the sum of the integrals. Okay, there's nothing here, right? And then now for this integral, with respect to x, what do we treat? What's the constant there in the integrand? What's the constant? That's right, Robin, negative 1 to the nth power. So we'll factor it out. Okay, we'll factor it out. You want to, you know, of course, this is showing good work, and these problems in WebAssign, the multiple choice ones, you have to be extra careful, right? Because you only have, if you have 5 choices, you only have 2 attempts. So, all right, and then the antiderivative of x to the 2n power is x to the 2n plus 1 over 2n plus 1. By the reverse of the power rule, plus a constant, and again, you're summing a bunch of indefinite integrals. Each antiderivative will have a little constant associated with it, but if you added up all those little constants, you would get this big constant here. So now Now, we have a formula for the arctangent. Okay, and so I'll move to the next page if that's okay. So far, we're good? All right, so now we have this formula. The arctangent of x equals this power series plus the constant. And what I've done is I've written out some terms for the series where I've written out the first four terms when n equals 0, 1, 2, and 3. And the interval of convergence, of course, would be x is between -1 and 1. We still have to solve for the constant c. So I'm going to let x equal 0. So this is something that I didn't have in the original notes, but we're going to put it in now. Let x equal 0. Then the arctangent of 0 is going to equal well, again, if I put 0 in for x, so what I'm doing is, I'm putting 0 in for x here. Trying to draw it as neatly as I can. This is the sum, of course. N equals 0 to infinity. Put the 0 in for x. What's that going to equal? So if you put the 0 in for x, what's the series, what's the summation going to equal? It's going to equal 0. So you get 0. Thank you, Josiah. Good. You get 0 plus c, which equals c. So c, then, is the arctangent C is the arctangent of 0 And what's the arctangent of 0? Zero. And so this constant here equals 0. Are there any questions on that? 0 is the most convenient value of x. It's a little bit like partial fraction expansion. Some of you, when you do your partial fraction expansions, I notice you pick certain values of x to solve for the unknown constants. And usually you pick nice values of x, ones that are going to make it easy to solve for those constants. It's the same kind of principle here. We're just picking a nice value of x so we can figure out what that constant is. And now we figured it out. So the arctangent of x will equal this power series, n equals 0 to infinity of -1 to the nth power times x to the 2n plus 1 all over 2n plus 1 when x is between -1 and 1. The constant equals 0. So now we know everything about this arctangent. We have the power series. Well, we know the arctangent is equal to this power series. And so in the problem here, when we see the arctangent, we can just substitute in the power series. All right, and so what I do is, what I've done though, with the power series, I've written out some terms, right, of the power series. I've written out some terms. The reason is because, yes, the arctangent of x as a formula is this power series, but equivalent to the formula, power series formula, equivalently I can write out some terms, the first 3 or 4 terms of the series, plus ... That also, well, I mean ultimately, right, like in WebAssign, they want the formula for the power series. But we know that writing the power series out as the first 4 terms plus ... that is equivalent to the power series. And so what I'm going to do then with my function here, is I'm going to replace the arctangent of x with this representation of my power series. And there's a reason I'm doing that. Let me let you copy it up to this step here, and let's make sure everybody's comfortable. Are there any questions so far? What nice thing happens in the numerator? What nice thing happens here? Something kind of nice happens. Is there any cancellation? The x cancels out. That's right, Josiah. So the x cancels out. And so we can express our function like this. And the minus distributes through the series. Hence, you have x cubed over 3 minus x to the 5th over 5 plus x to the 7th over 7th minus and so forth. Which is one reason I wrote the power series out I wrote my power series out, because then I could clearly see that the x cancels. It's just nice to do it that way. And now we have something that is certainly friendlier to work with, because now the x cubed, I can divide the x cubed into the terms up here, or think I can equivalently, I can multiply by 1 over x cubed over x cubed, top and bottom. And the series reduces to this series. Now, ultimately, we want to get a formula for the series. Are there any questions up to the last step here before we move on? Okay, all right. Well, we have to find a power series for, we have our series here, but we need to find the formula for its power series. So I've rewritten the step, and through just thinking, this is a formula here for the power series that will work. I'm not saying it's the only formula, okay? If you sometimes like in WebAssign, the help videos, the people doing the help videos, they might have a different formula, okay? But this formula works. If you put in n equals 0, n equals 1, n equals 2, you will have a match on this. Now let me just, yeah, you can check term by term. So it's always good to have at least 3 terms to just check that your formula is right. Are there any questions so far? Coming up with the series formula, there's no trick to it. You just have to detect the pattern. I saw a 3, a 5, and a 7. Okay. And I mean, up here you have even powers, so x to the 2th made sense. And then negative 1 to the nth gave me the positive, negative part of the series. And then 2n plus 3, I start at 3, and then I go 3, 5, 7, so 2n plus 3 worked. And now what we want to do is we want to then get the power series. So the integral of the sum is the sum of the integral. Here we go again. And I factor out the constant relative to x in the integral, which is negative 1 over 2n plus 3, a negative 1 to the nth power over 2n plus 3. and gets me to this stage here. So I'll give you a moment to copy that down, and please ask if there are any questions. So here's the function. And it's applicable when x is between -1 and 1. And we're going to leave the constant there, right? Because the function was an indefinite integral, right? That was our function. It was an indefinite integral with respect to x. So it's got to be a function of x. Okay, are there any questions before I move to the next page? Everybody has copied okay. May I move to the next page? Does anybody need more time? Okay, so here's the thing. Here's one thing I'll point out. So you get this answer, right? You get this answer, and let's say it's a multiple choice question. You get this answer, yet you don't see that answer in the list of choices. Okay, maybe some of the choices have n starting at 1 instead of infinity. Well, if that's the case, and like maybe a couple of choices start at n equals, the series for a couple of choices start at n equals 0, but you don't see any match to your answer. A couple other series start at n equals 1. Well, if the series starting at n equals 0 don't match your answer, then it has to be one of the series starting at n equals 1. So what you have to do then is rewrite this series starting at n equals 1. So if you do that, if you start the series at n equals 1, then you have to deduct 1 from n. Because, like, take -1 to the nth power. That first, when n equals 0, -1 to the nth power is -1 to the nth power is -1 to the 0th power. Okay, the first term of the series, this part of that term would be -1 to the 0th power. So if I'm going to then change my index to start at n equals 1, I still need -1 to the 0th power, right, to start off with. Right? One moment here. Let me move this. Okay. So like I said, when n equals for our series, the first term, the -1 to the nth power would be -1 to the 0th power. So when I change the index to n equals 1, -1 to the n minus first power when n equals 1 should be negative 1. I'm not saying this the right way. So the first term of the series, I've just focused on the negative 1 to the nth power. The first term of the series has negative 1 to the 0th power. So when I change the index to n equals 1, if I write negative 1 to the n minus first power, then when n equals 1, I get negative 1 to the 0th power. Okay, so that's like how I determine how to adjust n. So that tells me that, okay, anywhere I see an n, I replace n with n minus 1. Okay, does that make sense? I mean, is that understandable? Okay, so then if we do that, I can rewrite the power series for my function as this power series. And hopefully that power series would be one of the answers, one of the choices, if it were a multiple choice problem. So sometimes you have to do that. And there are reasons for that. For one thing, the course, the book, is testing you on your understanding of this, because rewriting of a power series with a new index is done often. You're going to see that when you get into differential equations, when you deal power series solutions of differential equations, you'll see this. So, okay, are there any questions on that problem? Good question, Josiah. The reason you don't have to solve for C is the original problem, well, f of x was equal to this indefinite integral. So there's going to be a function there. There's going to be a constant there because it's an indefinite integral. To be honest, I don't really need the f of x, right? That's sort of confusing. That's kind of, I mean, it's okay, but we don't really need the f of x. Well, I got to be a little bit careful here. Hold on. Let me go here. Let me just, yeah, we don't really need the f of x there. We don't need it. So in your notes, you can remove it. You can remove the f of x. Okay, or you can leave it in. But the reason you have a constant of integration is because you're getting a power series for an indefinite integral, so you need a constant of integration. Josiah, are you comfortable with that? Wonderful, wonderful, wonderful. Okay, okay. Are there any other good questions? Okay, let's do one more. Let's actually use a power series to evaluate a definite integral. And actually, let me just do one thing before you copy that down. Okay, on this last page here, you know, if you don't want to have the function there, just say that this equals, that power series equals the integral of x minus the arctangent of x over x cubed, right? That's fine too. That's fine too. That's actually, I think, that's how I prefer it, really. But, okay, let's move on. Now we want to use a power series to evaluate this definite integral correct to 6 decimal places. Okay, so why do we need to use a power series to evaluate this definite integral? Why do we need to use a power series? Why can't we just integrate? Well, can we integrate? Is there an antiderivative of x squared over 1 plus x to the 4th? Who thinks maybe not? Yeah, I don't know of it. I don't know of it. And if you were to look in the table of integrals, I don't think you would find one. So in order to, I mean, we know the function x squared over 1 plus x to the 4th exists. We can graph it from 0 to 0.3, and there will be some positive area underneath it. But we don't know, how do we find that area? We can't do the integral, but what we can do is we can substitute in for x squared over 1 plus x to the 4th a power series, and then integrate the power series. Okay, so let's go ahead and get to the solution here. So we start off, this is very straightforward. X squared over 1 plus x to the 4th. I'm going to, rewrite it using my Apple formula. The Apple is negative x squared over 4. And that means then that interval of convergence is x is between -1 and 1. Okay, so up to this step here, you've seen this before, this kind of manipulation of the, of the function. So I'll let you just copy that down and let me know if you have any questions. Okay, and of course, the x squared, I don't want that to be in front of the series. So let me bring that in. Okay. And then combine like terms, well, or, x squared times x to the 4nth power is x to the 4n plus second power. So x squared over 1 plus x to the 4th equals this power series when x is between -1 and 1. And you might notice that the limits of our definite integral fall within the interval of convergence. Okay, 0 and 0.3 fall within that interval of convergence. So using the power series to transform the integral, it's fine. Okay, so far so good. Are there any questions up to this last step here? All right, may I move to the next page? Are we good? All right, so next step now is we want the integral of our function. Hence, we need the integral of this power series. So we will do that. And we have the integral of a sum is the sum of the integrals. And you've seen similar steps like this in the previous examples. So I'm just going to kind of let you focus on copying it down and let me know if you have any questions. We should have some time for you to do some classwork today. So the book has nice examples too, by the way. Okay, so what I did was once I got the power series representation of my integral, I wrote out some terms. Okay, and so we can say then that the definite integral from 0 to 0.3 equals this power series evaluated from 0.3 to 0. Notice the indefinite integral here, there's a dot, 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 right? The indefinite integral, or the definite integral, I should say, I dropped the constant because now when you have a definite integral, you don't have that constant of integration anymore. Are there any questions? All right, I'm going to ask you a question. What kind of series is this? Plus x cubed over 3, minus x to the 7th over 7th, plus x to the 11th over 11th, minus x to the 15th over 15th. What kind of series is this? Terms are plus, minus, plus, minus, plus, minus, plus, minus. What kind of series do we call that? That's right, Michael. Very good. It's an alternating series. So this definite integral uses an alternating series, and therefore we can use the alternating series estimation theorem to help us get our approximation. Okay, and I'll show you how that works. Although you've seen it, you've used it before. But are there any questions up to this last step here before I move to the next page? All right, so what I'm going to do is I'm going to put in the point 0.3 in the series, and then I'm going to put in 0 in the series. So the definite integral will equal, this is here where I put in 0.3 in the series, minus, and now I'm putting in 0 in the series. But when you put 0 in the series, all right, so I put 0 in, all you get is 0, right? All you get is 0. Zero cubed over 3 minus 0 to the 7th over 7th plus 0 to the 11th power over 11 plus dot, 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 right? Dot, dot, dot. That's just gonna, that whole thing's gonna equal 0. Get the page number there. So the alternating, so what we have now is an alternating series, and we want it correct to 6 decimal places. Well, remember how you handle this. Correct to 6 decimal places means you want to find the term that's less than 5 over 10 to the 7th power. Okay, you want to find that term, and then the sum corrected to 6 decimal places would be what the sum of the terms that comes before that last term. So 0.3 to the 11th over 11 is less than 5 over 10 to the 7th. Again, we want correct to 6 decimal places, so it's 5 over 10 to the 7th power. If we wanted correct to 8 decimal places, we would have 5 over 10 to the 9th power. So the first 2 terms are not less than 5 over 10 to the 7th power. But the third term is less than 5 over 10 to the 7th power. So the sum of this series, this definite integral correct to 6 decimal places we only need to use the first two, add the first two terms of the series, which isn't hard, right? I mean, this, you know, remember mathematicians back, you know, 200 years ago, 300 years ago, you know, they didn't have TI-84 calculators, right? So when they needed to compute an integral, this is what they did, right? But mathematicians knew how to multiply and add, divide and subtract. And this is this 0.3 to the third over 3 minus 0.3 to the seventh over 7th. I mean, you know, you'd have to 0.3 to the third, you'd have to multiply 0.3 times 0.3 times 0.3, and that's what? 0.027, you know, 3 times 3 times 3 is 27, but you move the decimal point 3 places to the left. You all did this in elementary school, right? And 0.3 to the seventh, you can figure that out, and you can divide, you can do that. It takes time, but all I'm saying is this operation, 0.3 to the third over 3 minus 0.3 to the seventh over 7th, that can be done, you know, using fundamental principles and computing the integral using a power series. Well, the power series involves multiplication, division, addition and subtraction, and all of that can be programmed into a computer program, right? And you know, of course, it'll take a certain number of flops to compute the answer, but it's all programmable. And so this is very applicable to computer science. When your calculator gives you an answer, when your calculator, you know, if you compute a definite integral, how many remember the program where it shades the area in the calculator? You do a definite integral and you draw the picture and it shades the area inside and then gives you an answer. How many recall that? Yeah, Josiah knows, and I'm sure. Has anybody else seen that? That's John's seen it. Okay, great. Okay, and the computer magically gives you an answer. Well, how's it getting that answer? Okay, all right. Well, it's possible that it's using power series. Now, I want to be careful. I don't know exactly how it's getting the answer, but it's getting it somehow, right? And I mean, you did learn about things like Simpson's rule and you learned about numerical integration back in chapter 5, but this is also a way to get an answer. How many think this is absolutely cool? How many think this is really, like, yeah, John likes it. Just one person? Do we have any? Robin, great. Josiah? All right. Just 3 people? Anybody else? We have all men here. Are there any women that like this? Any of our female students? Okay, Suha likes it. And all right, I know we have more people here. All right. So this is actually a very beautiful thing that you just learned here. Very beautiful thing. All right, I'm going to stop the recording.